Hey, good day everyone. So what we'll be doing today is flow over an aerofoil. We'll do a cambered aerofoil, the most famous 2412 NACA 4-digit series. We'll do analysis for both the viscous and the inviscid flow, a part of your computation fluid dynamic laboratory. So to first get the data points for the aerofoil, we go to our very well known aerofoiltools.com website. So you can just type in the Naka series here itself. You'll be able to directly go to the airfoil generator. Now here, as you can see, this is your 2412 airfoil. The number of points by default they have given as 81. You can have it between 20 and 200. We'll go ahead with the maximum number of points so that your curve will be as smooth as possible. We'll also close the trailing edge. We don't want an open edge in our when we come to your design modeler. If we have an open edge there, we have to do a small sketch to close that as well. So we'll close the edge here itself and then hit plot. You'll get the new plot again. Now we will send it to airfoil plotter. Okay, now basically we did this to change the uh, chord value. Now it is at 100 mm. We'll make it at 1 meter. So typically any kind of 2D aerofoil analysis that you do, we keep the chord at 1 meter so that it'll be easier to do the Reynolds number calculations and every other calculation associated with an aerofoil. So with that, let's plot so that new aerofoil will be plotted for the 1000 mm 1 meter chord, and we will create a CSV file for these points. Now it's my downloads folder, not a problem. So I'll call it naka2412.csv. Saving it. Let me open that Excel now. Now in this page, we need to edit the contents here in this Excel sheet in such a way that ANSYS can understand. So for doing that, you need to delete all these. We'll delete all of them. We'll insert two new rows here. We will call this hashtag groups. This one hashtag points. This will be hashtag X. This will be hashtag Y, and there will be a hashtag Z as well. Okay, so groups are just to denote which curve it is. So we want this entire aerofoil to be a continuous curve. So we're going to name it as number 1, and we'll continue that numbering till the end of our aerofoil points. So I'll just double click here. It will generate till the end of our aerofoil points. Okay. And coming to the points, it's just a numbering for the points. So number of points. So 1, 2, so on till the 200 points that we have taken. And similarly, Z will be kept at 0 because we are doing a 2D analysis. So we need to define Z as well for the import function to happen properly. So these are the values that we have. Now if we come over to the last point, as you can see, this is the 201st point. Okay, so we don't need this point. We need this curve to go from 200 back to your origin 0 point. So we'll just give the origin again here. Okay, so this will be origin meaning the first point which is at 0, 0. Okay, so we'll go ahead to the origin location again. This is just a point numbering. We are going back to point number 1, from 200 to point number 1. Now there is some information about camber line and chord line, so these are not required for us. We will just delete them, so they are not relevant. So after this is over, we will save this file. We need to save this as a .txt for this to be open, so we will file save as, give the same name, but we'll have to select it to be a .text file, so txt. We'll keep it in the download section itself. So that's done, naka2412.txt. Now from here, we will go ahead and open ANSYS. We will take it fluid flow fluent, and then we will, before we go into the geometry, make sure that the analysis type here is set to 2D from 3D. Okay, we're doing a 2D analysis, so make sure that if this window on the right side is not opening for you, just right click on geometry and then click on properties. This window will open for you. Okay, now let me open design modeler. You can choose any of the other modelers as well. I'm very familiar with design modeler, so I'll go ahead with that. So in design modeler, we will try to import the points that we had. So concept 3D curve. Now they're asking for the coordinates file. So in that we will go and select our coordinates. So I believe it's under downloads. Let me see if I can find it out. Yeah, downloads and naka2400.txt. Open that. Well, there seems to be some error. Let me just take a look. Okay, so I figured out what the error was. So in the CSV or the TXT file, the last point you're supposed to give it as 0 so that it will go back to the origin. I only gave it as 1 here, so you're supposed to give it as 0 so that it will go back to the origin. Now if we again go to concept 3D curve, click on the coordinates file as our naka2412.txt. Okay, there's just an error. I don't think that it's fine. We'll select millimeter and then click generate. Yes, so we have generated the line body, which is our aerofoil here. So let's, okay, click on this. We can look at our aerofoil here now. Now for this line body, we have to create a domain for this aerofoil now. So to do that domain, we'll go into sketch. We will start off with having a C and a rectangular section here. That is what the domain that we'll be doing here. So for drawing the C, we will take arc by center. So as you can see, click or press and hold the center of the circle. So we'll start the center here and we'll give some nice radius here. Then we'll close that. So we'll go to dimensions. Let's go with the radius. So it's at 2.259. So it's better to have something like a radius of or a diameter of 15 times your chord, where chord being 1 meter. So we'll have a radius of 7. Okay, so that our diameter will be 15. So this is the edge or the domain edge for the forward section. The other section will have just a regular rectangle. So for that we'll go back to draw. We'll choose a line. We'll go ahead and draw this half of the rectangle. This half of the rectangle will bring it all the way down. Or let me draw this one first. And then we'll connect these two as well. Okay, they're not the same because we have some value differences. So let's go to dimension. We will select vertical. So from here, I'm sorry, this horizontal. So we'll go to horizontal from here to here, and also from here to here. Okay, so both of those has to be the same. So downstream, we will have something like 15 times the chord as well. So on both locations, so you'll get a nice proper domain here. Now before we create surfaces, we can also create a bounding mesh box for this particular system. Of course you can go ahead with this, not a problem, but if we do that, we will get a much more better result when we do the analysis. So in regards to that, so what we will do is I will go ahead to draw, take the line, similarly on the other edge as well. I will also draw one at this. Let me go to the edge here. vertical here, which will come down here as well. Okay. We have some point here for some reason. Let's take that out. Seems to be some kind of glitch here. It's not required. So we'll have to extend this to the and extend this to that end. Extend this as well. The other end as well. Okay. Can take trim. Okay, when we take the surface off, it'll be fine, and we'll extend these as well. Okay, and we need them to be at a distance of exactly 1 meter. It's not yet that, so I'll give that value here, and we'll have this one to be exactly at a distance of around 0.1. Yeah, well, I think 0.1 is fine. Okay, so this is our domain. Now let's create the surfaces. So creating the surface, we'll go to create a surface from edges, a surface from sketch edges. Yes, we'll select the aerofoil first, apply, generate. So I created the aerofoil. Next we'll do it for the domain as well. So create surface from edges. Since this is a sketch, we'll have to create it from the sketch. So concept, surface from sketches. We select these lines by holding control. Right, and then we can click apply and then click generate, so we get that as well. Now we need to remove this aerofoil, so for that we'll go to tools. We'll have something called boolean. I believe it's in create boolean. Operation is okay, so we change this unite to subtract. Target body, apply. Tool body is this one. If you can't select it, you just have to click this, we select it, apply, and then click on generate. Now you can see there is a hole here where the airfoil used to be. So this is where the analysis will take place for us in this particular location. Okay. Now since this is done, we will save what we have created here. Call it airfoil flow. We'll close out design modeler, saving precious resources, and we'll go ahead with mesh. The meshing is starting, so whatever process is happening, you can see it on the bottom left corner here. We'll have to wait for that thing to complete. It's taking quite a lot of time to open meshing. I think before we go to mesh here, I forgot a small step where I had to split the um, faces of the surface. So I think we'll go ahead into design modeler, complete that, and then we'll come back here. Okay, so we'll close meshing for now. We'll open up back geometry. And we are starting design modeler again. There's one more step where you have to split the entire face of the domain. So let's look at the ZXY. So this is the part that we have with some, okay. Okay, so we have, okay, so what we'll do is we'll go to concept, well it's in tools, yeah, tools, face split. So click on this entire face. The tool geometry is going to be all these separate edges that we have. To click that, change this selection to edge selection. Click on all the different edges that you would want this to separate by. Okay, so these are all the edges that I would want it to separate by, and then click apply and then hit generate. So now if you select the face selection filter here on the top, you can select all these faces individually. So this will be helpful when you are doing the meshing. Okay, so we'll again save the design here. We'll close out design modeler and we will go ahead into mesh. Now since we have already made out broad sections for the meshing, this meshing will be much more easier for us. I'll show you how this can be done. It is not mandatory to do it, but it gives you a better result. That is the only thing we are aiming for here. Okay, now we don't need this. Geometry has been updated. We have the surface body here. So we don't need the line body anymore. We can suppress that. So we are only interested in the surface body here. Okay. Now to mesh, what we'll do is we'll write it, give sizing. For the geometry selection, we are going to be selecting each individual edges here. Okay, so I think we can select these, control and select these three, and we can even select these as well, all of these edges, and we are going to give apply. Instead of element size, we are going to make it number of divisions, and we'll give this divisions as maybe 250. So 250 divisions will be created on all these places. I think it's too much. We'll go ahead at 200, and we will give biasing as well, a bias factor of 2 maybe. So basically we'll have there is some reverse biasing happening here, or maybe let's go ahead and basically this, why we do the biasing factor is to get more number of cells around the aerofoil and then less amount of cells near the inlet, because we don't need much of an analysis here. We're only trying to see what is the performance of this particular aerofoil. So maybe right now we'll just leave off the biasing. We'll just give default 200 to everybody. Then we'll create another one more mesh sizing for the other locations here. So for the top edge here, let me see if I can, I'll go to that selection, the top edge, the middle and the bottom, apply, again go to number of divisions, and we'll go ahead with 300 here. Okay, then we'll go to the next edge, sizing again. So this will be this one, this one, this one, and this one. Okay, so apply those. Again, we will be going with number of divisions. We'll give the divisions as 50 maybe. I think that seems sufficient for this location. Right? Now, okay, for this edge sizing, we have selected these edges. Okay, fine. Everything seems fine, I believe. And also, we will add one more uh, match control. I think it used to be called the face mesh. So we will select, sorry, it's a different option. Okay, we have face meshing here. So click on that and click on all the faces that we have in this domain. Click apply, and then we are ready to mesh with the generate mesh button. So given a lot of divisions, so we'll get a very okay, very stylized way of getting the solution here or the mesh here. So this happened because we did not give any values or divisions here in this edges. Maybe let's correct that as well. So we did not give any values here. Okay, so that was the issue. So we'll go ahead with sizing. We'll select this edge and this edge, and we'll give number of divisions. I believe we gave number of divisions as 200 for each of them. So let's do the, we can have 200, maybe we can have 50 again. So let's try to mesh you now, generate mesh again. Okay, now it's much more better, but it could be more better. So we will go ahead with what we have now. Okay, we are not worried about the inlet, so it doesn't really matter. We're only worried about what is happening near the surface of this airfoil and the outlet. Okay, so that the meshing is done now, we need to create some named selections here. So after selecting these edges, we're going to call these ones create named selection as inlet. We're going to be selecting these two sections create named selection as the outlet. So this is going to be our create name selection airfoil. Okay, I believe we named all these sections, right? Inlet, outlet, and the aerofoil. So remember, all the other lines are just guidelines that we had done to make this meshing as good as possible. They won't be coming in the final solution of your analysis. So that now the terminologies have been given. Okay, now that we have completed the meshing, we can click on update. That will be updated outside. Okay, yes, and we can save it, and then we'll go back to the workbench. That is still not yet updated here, so let's just right click here. Okay, so the mesh is also updated. You get a green tick. Now let's go into the setup. Now for the setup, there will be a box that pops up when you select this particular button. We are just waiting for that. It's a start screen for the Fluent system. So of course we are doing a 2D analysis. We can switch on double precision if we need. If you know the number of solvers in your system, you can select that as well. So let's give 4 here. and click on start. This will open up Fluent now. All right, now that Fluent has opened, we have our mesh domain here. So let's check the mesh. It's done. We can check it how well the mesh has been done. We do the same thing in OpenFOAM as well. Now this is going to be a pressure based solver. We are going to leave it at planar. A steady state condition is fine. So going into the first case of models. Now here, right now the SSTK omega, we don't need that. Okay, so the two experiments that we're doing is one is inviscid flow and the other one is viscous flow. So for inviscid, you just need to click on this and then proceed whatever we are doing right now. If you want to do any other kind of viscous related flow, any of the other ones you can select. Typically, we will go for the laminar flow. Okay, so that's what we will go ahead now. Of course, for the other experiment, you just need to click on this and then follow the same procedure that I am doing. So this is more than enough. So it's laminar. Okay, we have set that. Now it's time to set the materials, which is fluid, and we are going to have air as the medium that is flowing. We're not going to make any changes to the density or the velocity of air. So that is with respect to your materials. When you come to your boundary conditions, aerofoil is a wall, so we don't have to do anything there. Inlet, we'll have to give some values to it. So it's a good practice to go for the magnitudes and directions so that you can very easily give whatever values you need in the proper direction. So you want to enter the velocity here. So let's say the velocity is at 10 meter per second. Okay, so give it apply, then close. Similarly, if you go to the outlet, outlet is going to be pressure outlet and it will be completely empty. Yes. Okay, the gauge pressure is 0 basically. Now that the boundary conditions have been set, the next thing that we can do is okay, now we don't need that. Yeah, we'll go into the reference values here. Now this we will compute from the inlet, only the velocity will change there, and then we can straight away go into solution methods. Now here we're using the coupled scheme. We can make changes to this if required, but for now we'll just go ahead with whatever is given. We can change these values if required, pressure, momentum, and density, body force as well. Now, if we go into report definitions, we are going to take a look at the coefficient of lift especially. So we'll do a coefficient of lift as well as a coefficient of drag as well. So for that, you just need to click on new force report, drag. Okay, we'll name it CD, capital C and small d. So we're going to have caps here. Okay, capital C and CD. Now this is in the location 1, 0, which is the location where your drag is going to act, because drag always acts parallel to the flow, and the flow is in the x direction itself, 1, 0. This is the pattern where the flow is flowing, and this is the x direction that you'll be taking in as it is given here. Now this CD we are going to be plotting for the aerofoil. So click on that, give OK. That is done. Similarly, we are going to do a lift report as well. We'll call it CL. Okay. Now for this time the y direction, because lift is usually perpendicular to the flow. So that's why it's 0, 1. So again we're going to select the aerofoil. Remember, this is coefficient and not the force. You can select force if you want, but this is by default set to coefficient. Click on OK. Now that both the reports have been defined, you can come out. You can go into monitors if you need to change anything. You can go into the residuals here. Now it's at 0.001. You can make it much more better as 1 e power minus 5 if required. Similarly, you can copy paste to the entire domain here. Okay, now that is done, residual and these plots are done. Let's go into the initialization. So you can do a hybrid or a standard initialization. So let's just do a hybrid for now. Okay. Now that it has been initialized, let's go ahead with the calculation activities. I think it's still initializing. Okay, now the initialization is complete. Hybrid initialization is done. We'll go ahead into the calculation activities. Now here, if we need to or save these iterations every minute, we can give the command here. We don't necessarily need to do that. So we'll go ahead to run calculation and we'll give the number of iterations as 500. Let it input every 1 or 10 iterations. And then you can click on calculate. So this process will start to run for 500 iterations. We'll just wait for the program to start and then I'll skip ahead to the end. Okay, now it is running. As you can see, yeah, the continuity x and y velocities here. The iterations running in the bottom. Here you have the CL and the CD plot. The CD has turned out to be almost constant here, as well as the CL. So this is a good result. Now what happened is, okay, we'll just pause for the solution to simulate to the end, and then we will get back to when the simulation is completed. Okay, so we got the calculation complete button here. So as you can see, the solution converged in the 90th iteration. So it's very well for us. Before the we gave 500 iterations, but in the 90th iteration itself, the solution converged. Something you have learned in the numerical methods, right? So now we can go ahead and see all the results now. So if we go to surface here, we can click on the, let me go ahead into graphics. We have the contours. Yeah, so we'll do a contour of pressure, static pressure, aerofoil. So this get on display. You can see for the aerofoil. If you want to see for the entire body, yes, you can click on this. You'll be able to see the simulation. Okay, now this is in wireframe. We can remove that if required. We can make it a smooth contour also. Similarly, we can check out the velocity as well in velocity magnitude wise. Okay, so this is the velocity that you can see. Okay, so in such a way you can visualize the pressure and the velocity. Of course, you can go to ANSYS CFX to do a better post-processing analysis if required. Now for our case, what we need is the converged CL and the CD. So of course these values you can see straight from the graph here. It's around 0.2518, which is your CL that has converged. You can also find that same value if you had set up a report system for this CL and CD value. You can take from that as well. Of course, you can always take from this graph. The CD is at around 0.0056. These are some expected results for this particular simulation. Now, let's say you want to change the angle of attack for this. So you don't necessarily need to go and draw the entire thing again. All you need to do is come to the boundary conditions, go into the inlet boundary conditions, okay? And here we again magnitude and direction velocity at 10 meter per second. Yes. So what we will do here is we'll change this into components, and now we have, okay, in the components you'll have x velocity and y velocity. Again, we are in 2D, so we don't have anything to do with z here. So x velocity and y velocity, what happens is if you're going for an angle of attack, basically let's say you're doing 5 degrees now. So 5 degree will amount to the resultant wind flow that is there. So if you want to organize that here in terms of x and y velocity, because that is a component of velocity which is at an angle of 5 degree with your aerofoil. So if you're considering that particular case, if you want to change the angle of attack to 5 degree, the easiest way to do that is using the values here. So in x velocity, again these are just trigonometric relations that we're developing. So in x velocity, you will have the value as velocity times cosine of your angle. Okay, so if the velocity happens to be 10 degrees, sorry, 10 meter per second, multiplied by the cosine of your particular angle. Okay, similarly for y velocity is going to be your velocity of that particular object times the velocity here, sorry, the angle here, okay, through the sine. Now if we, let me quickly do that calculation. Okay, so the cos of 5 degrees around 0.99. So if you're multiplying it by the x velocity, which is at 10, so you'll get 9.9. And for sine 5 degree, it is around, we calculate that once again. 5 sine is around 0.087. So if you multiply it by 10, which is your velocity, 0.87. Okay, so this will be the velocity in the y direction. Just click on apply. You can close this, go back to your reference values, again change it from inlet, the value of velocity will change, and then go back to initialization. You can click on hybrid initialization. Yes, you can initialize. That is done. And again, you can go into the run calculation section here. You're going to run calculation. Same thing we can set up. Maybe we'll give 100 iterations now, and then click on calculate. So once the calculation is done, we'll be able to see the final results of what we require in this particular flow system. Now this is for a 5 degree angle of attack. So let the simulation run. We'll come back to the results. Simulation is progressing ever so smoothly. Okay, again at 90 90th iteration, our solution has converged. I think it's still about to close. Let's just wait for it to complete, and then we'll okay, so the calculation is complete. We'll click on OK. Now as you can see, there is a change in the CD and the CL plot. Now our CL is somewhere near 0.72. Yes, so you can see a drastic change when you change the angle of attack, because this is a cambered aerofoil. You're getting a really high lift as well. At the same time, since again we are using a cambered aerofoil, we had lift for the zero angle of attack as well. Yes, so that can be visualized here. And to see the contour again, you can, okay, we do have the contour already here, so you can just see and display that here. Okay, So as you can see, the angle has changed, right? So from far off, you can see this change in the angle. So this corresponds to the 5-degree angle change that we have done. Okay, that is fine. Now, to study the CL and the CD values that we require, I had to make one more change before the calculation, which I did not show you here. So under reports, I'm sorry, okay, under reports here, report files here, we have CL and CD, right? So these have to be modified because we go to here, yeah. So these have to be modified because they are written for, as in the case of a 1, 0 setup. Okay, so that is not what we need basically. Let me collect, yeah, CL. Okay, it's asking me to, that is not what I want to do. Maybe let me go to monitors. I seem to have uh, missed something here. Report definition. Okay, this is what I have been searching. Sorry about that. So research report definitions. Now here CL. Let's start with CL. Edit. Yeah. So this is at 0, 1 for the left. Now that is going to be not going to be the case because left has been the perpendicular direction has been changed in accordance with the angle that we have given. So instead of 1, it is going to be here sine of that particular angle, which is around 0.087. Okay. Similarly, when you take your CD, this is at 1, 0. Again, instead of that 1, you will have your 5-degree angle component, which is 9.9 basically, right? I'm sorry, 0.99 is the cos of your 5-degree angle. So that is what will come here. You can click OK, close. Now you run the entire simulation, you will get proper Indian results. This is how you have to transform and learn. Okay. So thank you everybody for listening in. Like I said, for both inviscid and viscous flow, this model can be performed. So I thank everybody for watching the session today. Thank you.